All right, so we're looking at an introduction to matrices today. So matrices are just a more convenient way of dealing with systems of equations. And I know that when you first learn matrices, they seem overcomplicated and it seems like this isn't any better than what I was doing before. And if you're dealing with a system that is two equations and two variables, yeah, it's about the same amount of work either way. But as your systems of equations grow, as they do in the real world, rarely in real life are you doing a two equations and two variable systems of equations. Oftentimes they are larger, much larger. When I was in grad school, I was dealing with systems of equations that were thousands of equations, thousands of variables. At that point, you really want to be able to put them in the form of a matrix, and it stands to reason you're not usually doing this by hand. Oftentimes you're having computers handle these systems of equations for you, and most computer software that handles systems of equations is programmed to do so in the form of a matrix. So matrices are hugely important for using computers to get computing done, which is how a lot of this stuff gets done. So it's an important topic. Now, I mentioned that a lot of times you have computers doing the systems of equations for you, which is true, but you have to understand how to get your system of equation into a matrix and into the computer, and then you have to understand how to interpret the result that the computer gives back to you after it's gone through and done whatever you're having it do. So let's take a look here. What we're starting with is a system of equations on the left, so this should look familiar. X plus 1 equals 1, 2x plus 3y equals 6. That's just a system of equations, right? Well, what we do is we translate this into a structure where the columns are variables. So columns go up and down like in a building, right? Columns are vertical. And then the rows are horizontal, like on a farm, they plant in rows. Those are horizontal. The rows represent equations. So a row is an equation, a column is a variable. So you can see right here, here's how we translate this system of equations right here into a matrix. So we make the first column be our x's, the next column is our y, and we only have two variables, so we only need those two columns. And then this last column is the constants that your equation is equal to. So you can see what were our excuse me, our x coefficients are 1 and 2. So we can see right here we have 1, 2. Our y coefficients are 1, 3. So we can see if we have 1, 3. And our constants here are 1 and 6. And so we go 1, 6. And this line right here that you see, we're left with this over here. That's going to be where we put the equal sign. Right? So where the equal sign goes, that's just kind of there to help us remember that's what the equal sign is representing. So when you write an actual matrix, you don't write all this extra stuff I have here. You don't write equation 1, you don't write equation 2, you don't write x and y. I'm just putting that there so you can see what the columns and rows represent. Okay, this is what your actual matrix should look like. So you should be able to look at this and say, oh, this is 1x plus 1y equals 1 and 2x plus 3y equals 6. So it's pretty basic, pretty straightforward. Once you've seen the explanation, most people are pretty good at going back and forth. Taking a system of equations, turning it into a matrix. Taking a matrix, turning it into a system of equations. So you'll want to do that. That's kind of the basic thing that you have to be able to do. Okay. So like take this for instance. This is actually a form this is actually kind of our target form. This is what we want our systems of equations to ultimately get through, because see this form we have right here where we have ones on what's called the diagonal. So the diagonal is created by where the row and column are equal to each other. So in other words, in the first row, first column position, that's this term right here. In the second row, second column position, that's this one right here. In a bigger matrix, there would be a third row, third column position. So those are considered the diagonal. We want ones on the diagonal. So ones where the row and column index are equal to each other. First row, first column, second row, second column, we have ones. And then we want zeros above and below those ones, like this. See how we have zeros above and below them? And then over here we have a 2 and a 3. Why is this desirable? Because this is the solution, right? How would we read this? We would read this as 1x plus 0y equals 2, which is just another way of saying x equals 2, right? You can see I've got the answer written over here. This first row reads x equals 2. 1x plus 0y equals 2. Now 0x plus 1y equals 3. That simplifies to y equals 3. So when you get your matrix in this form, where we've got ones on the diagonal, zeros above and below it, and your last column is constants, that's your solution. You can just read the solution right out of there. Right? Now, notice I don't have the line here representing the equal sign like we did up here. I just, you'll see it both ways. So a lot of times you'll see the matrix. This is technically called an augmented matrix, where we have the line here where the equal signs go. But a lot of times people just don't put them in there. So it doesn't really matter if it's there or not. You know what the matrix is representing. So like a lot of times when you first start using MATLAB or Maple, by default it doesn't put that line in there. You can force it to. But a lot of times people just don't take that extra step, but we still interpret the matrix in the same way. So how would we interpret this one right here? Well, this would be 1x plus 0y plus 0z equals 1, or x equals 1. 0x plus 1y plus 0z equals 2, or y equals 2. And 0x plus 0y plus 1z equals 3, or z equals 3. All right, once we have a matrix, then we have 3 row operations that we can apply to the matrix. And this allows us to manipulate the matrix to get it into that form that we wanted. The form where we have ones on the diagonal and zeros above and below those diagonal entries. That's what we want to get to. So how do we do that? We do that with 3 row operations. So we've got this row operation. The first one says 2 rows of a matrix may be interchanged. In other words, we just take 2 rows and we switch them with each other. So we could just switch the top and bottom row. Why is that allowable? It's allowable because it's the same as taking your system of equations and just switching the order of the equations. That's not going to change anything, right? So that's pretty reasonable. That's one operation that you get to do. And we can see that right here. We have the matrix 1, 2, 3, 4, 5, 6, and we swap the 2 rows to get 4, 5, 6, 1, 2, 3. That's just row operation 1 being applied to this. Row operation 2 says we can take the elements in a row. The elements in a row may be multiplied by a non-zero number. So this is allowable because this is the tool we've been using for a long time, where you multiply the entire equation by a non-zero value. That's what we're doing here. Because remember, the row is representative of an equation. So if we multiply the entire row by the same thing, that's the same as multiplying the entire equation by the same thing. So that's what we've done here. We take row number 1, 1, 2, 3, we multiply it by 2, and we get 2, 4, 6. Okay? So we get that right there. And our third row operation, the elements in any row may be multiplied by a non-zero number, and these values may be added to the corresponding elements in any other row. So that sounds complicated. What it's saying is we multiply one row by a non-zero value, and we add it to a separate row. Okay. This one is kind of like when you're doing the elimination or addition method for systems of equations. What do? You take 2 equations and you add them together. That's basically what we're doing here, except we're adding a multiple of one row and adding it to another. Okay. So let's take a look at these in action. So let's kind of go through this. What do we have here? We've got, let's give myself some room here to make sure I'm not blocking everything. So we've got the system of equations, 2x plus 3y equals 5, and negative x plus y equals 5. So we want to write the matrix that represents that. Well, we just take these coefficients, 2, 3, 5, negative 1, 1, 5, and then we put them into a matrix right here. Right? Now, remember, you have to be consistent. So if your equations are kind of jumbled up or not organized, you have to get them into this standard form. But once you do, it's just a matter of creating the matrix from those coefficients. Okay? So let's work through this. This is actually using those row operations to solve a system of equations. So we've turned it into a matrix. And what do we do here? Well, remember, it's important that we do our steps in the right order. There's more than one way to do it, but you want to make sure that you have certain goals set for simplifying this matrix, because if you do it in a bad order, you're going to end up undoing some of your work. So what you generally want to do is we start with the first column and we get a 1 in the correct position, and then we get the zeros for the rest of that column. Then we move to the next column, get the 1 in the right spot, and then get the zeros where they go. And then you just successively go through your columns from left to right, putting a 1 in the right spot and then putting zeros elsewhere. It's tempting sometimes to go, ooh, I can like do this one step that's coming up. I'll just take care of it now. The problem is by the time you get to that step, you've probably undone that work. So it's better off just taking care of it column by column by column first, and then you don't undo any of your previous work. So remember, our goal is to get a 1 in this first row, first column position. We want a 1 right there, and right now we have a 2. So what I'll tell you is there's more than one way to do this, right? There is definitely more ways. So if you're watching this and going, oh, I would have picked another row operation to get a 1 there, that's fine. Go ahead and do it. That's fine. Okay, but our goal is like here to get a 1 in this position. So what I did here, partly I did this just so you could see the row operations in practice. I'm going to swap the 2 rows here. So we do a row swap, and that puts a -1, 1, 5 up at the top because we swapped it from down here. We just swapped the position. Okay, so what is D? What do we do to get from here to here? Well, I can use row operation 2 and just multiply the entire original row by -1, and then I get this, and now we have a 1 where we wanted it. That's great, right? Now, how do you get the zeros? Once you get a 1 in the right spot, how do you get zeros in the rest of the column? You're almost always going to use row operation 3 to do this, because what you're going to do is you're going to take a multiple of this row that has a 1 in it, and you're going to add it to this row. Which multiple do you add to that row? It's whatever's going to give you a 0. So if I take -2 times this top row and add it to the bottom row, then -2 plus 2 gives me a 0 right here in that position that we want. So that's what we do. We take -2 times the top row, add it in here, and it gives me 0, 5, 15. Great. Look, how our first column is totally taken care of. And now that we've taken care of that column, our work is solidified. It's not going to get undone unless we do something really crazy. Okay? So that's great. That one's already taken care of. Now we look at the next row, or the next, we go, okay, what can we do over here? Well, I want this 5 to become a 1, right? Because that's the second row, second column position. Well, it looks like I could just multiply this entire row by 1/5. If I do that, I get 0, 1, 3, and look, we get a 1 right where we want it. That's awesome. So then what we're going to do, row operation 3 again, I'm going to take 1 times the bottom row and add it to the top row. And here we have that pattern that we like. 1s on the diagonal, 0s above and below the 1s. And now we have our solution, and we can just read the solution out here. This reads x equals -2, y equals +3. And we could go back and plug that into our equation and see that it works. Okay, so that's those row operations in action.